6.7, the recursive rule for sequences. Now, we can look at our example here for example number 1 that we have we look here and we can see that it is an arithmetic sequence that +2, +2, +2. So our common difference, D, is 2 with our first term of a sub 1 as 3. Now we can then use that to write our equation that we've been working with, which is the regular form is a sub n equals a sub 1 plus that difference times difference, which is that number minus 1, so that 1 less than the number of our that we want in our sequence. So if we go up here, we can write that as a sub n equals the first term, which is 3, plus n minus 1 times our difference, which is 2. And then we can simplify that. A sub n equals 2n, and then 3 minus 2 is plus 1. So this rule here is what we call an explicit rule. So our explicit rule for this sequence is a sub n equals 2n plus 1. So we'll label that down here, explicit rule. Now we will get into the recursive rule for each of these. Recursive rule. But I want to go do the geometric one, geometric sequence. So I can see that if I take the 50 divided by 10 is our ratio of times 5, which is that r. So our geometric explicit rule for our geometric sequence is a sub n equals 2, is a sub 1 r to the n minus 1 power. So if we bring it back up here, we'll have a sub n equals 2, our first term, times r, or times 5 to the n minus 1 power. And that is the explicit rule, the geometric explicit rule. Now, the recursive rule follows some of the similar numbers. We use the same numbers, we just use them in a different way, in that we look more at the differences and each difference between those, or the difference. So what we do is we start with a sub n again. And so the recursive rule will be a sub n equals. Now we're going to start with the number before n. So we do that by showing it in a subnumber n minus 1. So it's the number before our number that we want, and then adding our difference to that. So we're still using the difference, we're still using the number, our first number. We need to start with our first number. So that's kind of where we have to kind of start. I put a question mark here because each sequence starts at a different number. So up here at our recursive rule for our arithmetic one would be a sub 1, which is our start number, was 3. And to get the next number in the sequence, we take the previous number, a n minus 1, that number in the sub, plus our difference of 2 here. So that is the recursive rule. And we can kind of see if if we kind of want to find the second number, a sub 2, we would take a sub 1, so 2 minus 1 is 1, so the first number, which is 3, and then we'll add 2 to that recursive part. So a sub 2 would be 5, and we can see that in our sequence, it would be 5. To get to the third one, you would need to take an a sub 3 equals a sub 3 minus 1 is 2, so you take the second one, 5, plus the 2 difference to get 7. Now you'd have to have each one before that, so if you wanted to do the 10th one, you'd have to have all the recursive ones before that. So for the geometric, it follows that same kind of pattern where you need the first number, and then we're going to start with a sub n equals, same as before, is going to be the ratio times our a sub n minus 1. So we're going to take the number previous to the number we want and then multiply it by the r. So it's very similar to the arithmetic. Instead of adding the difference, we're going to multiply by that ratio. So to write our arithmetic or our recursive rule for our geometric sequence up here, a sub 1 equals 2, and then we'll start with a sub n equals, now our ratio is 5 times a sub n minus 1. So to find, say, the second term, a sub n, we would need to take our 5 times, and then 2 minus 1 is 1. So a sub 1 would be 2. So 5 times 2 is 10, and that would be our second term in our sequence. So this recursive rule is very similar to our explicit rules, just in a slightly different way. And so what we're going to do is use those two in different ways and going back and forth. So if we take a look at an example, if we have, so for number 2, a sub 1 equals 2, and a sub n equals a sub n minus 1 plus 3. So if we take a look at this, what's given to us, it's the recursive rule, and because it's a plus 3, that's our difference. So this is our difference, and this is our a sub 1. So to find the next, say, 6 terms, so up to the 6th term, we would take and start with a sub 1 is 2. So to find the second term, a sub 2, we would take a sub 2 equals, and then kind of substitute into here. So a sub 2 minus 1, which is 1 here. So a sub 1, which is 2. So I'll substitute my 2 in for that one, plus my 3 is that difference. So 2 plus 3 is 5. So a sub 3, so our third term would be that a sub 3 minus 1, which is 2, and the second term was 5, so we'll substitute a 5 in there. 5 plus 3 is 8. A sub 4, now we kind of have that pattern of plus 3, would be 11. 14 would be a sub 5. A sub 6 would be 17. And then that would be our sequence of numbers for this recursive rule. For the geometric one, given a sub 1 equals 1 and a sub n equals 3a sub n minus 1. So remember, there's multiplication between the term before and 3. So we'll start with a sub 1, which is 1. And then to get the second term, we take a sub 2, which is then 3 times a sub 2 minus 1, which is 1, and a sub 1 is 1. So 3 times 1 is 3. A sub 3 then would be a to the sub 3, so the third term would be 3 times a to the 3 minus 1 subnumber. So that would be 2, the second term, which is 3. So we'll substitute 3 in. So 3 times 3 is 9. And we can see that recursiveness happening. So we'll use that. So we'll take the second term, thinking in my head, second term times 3. So a sub 4 is the 27. A sub 5 is that term before 27, which would be this number, pink number over here, times 3, which is 81. And a sub 6, 81 times 3, the previous number, 243. And that would be our geometric sequence for our using that recursive rule. So now we want to practice how to write the recursive rule. So if we're given a sequence of 500, 100, 20, 4, 0.8, ... All right, so we'll look at, well, it's not arithmetic, so let's test to see if it's geometric. So that would be, I'll start here with the 4 and the 20. So 4 divided by 20. Okay, so that would be a times 1/4, 1/5. Yeah, because it'd be 4 over 20, which would be 1 over 5. Now, if we go 20 over 100, that would also be times 1/5. And 100 over 500 is times 1/5. So that is our R value, our ratio. Not the R value, but the ratio. So to write that recursive rule, we need to have our first term of 500, and then we'll have a sub n equals, and if I kind of remember up above, it was that ratio first, the multiplier, times a n minus 1, because it's times the previous one. So it's that previous number, say 20 times 1/5 would equal the 4, the n number. So if we take a look at another example, -30, -18, -6, 6, and 18, ... So in looking at this one, I see that it is more arithmetic. So let's just plus 12, and it's a plus 12. So our common difference is 12. So to write that the recursive rule, we'll have to start with the first term, -30, and we have a sub n equals, and then here we'll start with the term a n minus 1, the term before, and we will add that difference to it. And then there is our recursive rule. Now, if we go to a little more complicated, we're going to start with a recursive rule and go to an explicit rule. And then we'll do it the other way around. So, example 6. Given a sub 1 equals 25 and a sub n equals a sub n minus 1 minus 10, we have some information that we need to look for. So let's go, this is minus 10 would be our d. D equals negative 10. And we have our first term here. So now we can write our explicit rule. A sub n equals a sub 1 plus n minus 1 times that d. So a sub n equals 25 plus n minus 1, and our difference is a negative 10. Now make sure that you put that into parentheses, otherwise it's going to look like a minus 10 when it should be a times negative 10. So now we can simplify our equation. So 25 plus negative 10n plus 10. So a sub n equals negative 10n plus 35. And that would be the explicit rule for that recursive rule. Number 7. So if we're given a sub 1 as 19.6 and a sub n equals negative 0.5 a sub n minus 1. So this tells me that it's a recursive rule where this negative 0.5 is our ratio, and we've got our first term. So to start off with, our a sub n equals a sub 1, because that was our initial number, our first number, and then we have the r to the n minus 1, because that would be getting it to that first term. So a sub n equals a sub 1, which is that 19.6. R is negative 0.5 to the n minus 1. And what's nice about that one is there's not as much simplifying. That's what I like about this. All right, so now we're going to go from the explicit, given the explicit rule, we're going to write a recursive rule. All right, so example 8. If we are given a sub n equals negative 2n plus 3. All right, so we know that that negative 2 is our common difference. That's what's the change is gonna be. So we need a sub 1. And a sub 1 is when, we could just use our equation. So n is 1, so I'll substitute 1 in for n and simplify. So a sub 1 equals 1. So what we'll do is negative 2 plus 3 is 1. So we will start our recursive rule. A sub 1 equals 1, comma, and then a sub n equals, and then we have our number before plus our difference. And it's a negative 2. So we could write a minus 2 or plus a negative 2. And that is that recursive rule equivalent to the explicit rule. If we look at another explicit rule, a sub n, and you'll never guess what's coming. Yeah, that's right, geometric. And 2n minus 1. So we know that the 2 is in the place of the r, and this negative 3 right here is our a sub 1, because it's a sub n equals a sub 1 r n to the negative 1. So to write our rule is a sub 1 equals negative 3. Now we can think about this. Why is it negative 3 the first term, because if we think about a sub 1 equals negative 3 times 2 to the 1 minus 1, and that's 0 exponent, so that's 1 here. So 1 times negative 3 is negative 3. So that's why a sub 1 is negative 3. Also, or the reason why it's negative 3 is the first term. A sub n equals, now we start with the recursive rule, so times 2, and then we multiply it by the previous number for the recursive. And then we've got our final answer here. Now, you might be asking yourself, well, why do we have two ways to write the same one? Well, a lot of what we do in mathematics, or a lot of the problems we've solved so far, is in linear, is very and exponential, can be written as an explicit rule. But there are problems where, special cases, where you can't write an explicit rule. And that's why we have this recursive rule. So we have a recursive rule for special cases. And they're just different because you can't write them as kind of the explicit. So here's an example of one. And 1, 1, 2, 3, 5, 8, dot, 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 and so on and so forth. So we can take a look at it and go, well, let's see if it's arithmetic. So we can kind of look at that. That's a plus 0, plus 1, plus 2, no, plus 1, plus 2, plus 3. Oh, very interesting. But it's not arithmetic. So let's take a look at it if it's geometric. So that would be a times 1, times 2. This one would be a times 3 over 2, so the term divided by the previous term. The next one would be times 5 over 3, and the last one would be times 8 over 5. And so it doesn't work for arithmetic, doesn't work for geometric, but there is a pattern here, and we can kind of see what happens here. Oh, I kind of saw what the adding, there's something kind of interesting that happens. So if we think about, how do you get, say, the third term? So how do you get this third term of 2? Well, we kind of look at like the pattern and go, oh, it's the 2 before it. So 1 plus 1 equals that 2. So a sub 3 is 2. A sub 4 is 1 plus 2, which was the third, number 3, or 3 is the fourth term in that sequence. The fifth term was the 2 plus the 3 equals 5. So it's the two previous ones added together to get your term. So 8, to get 8 for the sixth term, would be 3 plus that 5 equals that eighth term. So now we can kind of think about, well, how do we get the term before it? So if we think about this and rewrite it, so this would be the two terms before it. So this would be term 2, a sub 2, and this would be a sub 3. So it gets a little kind of messy here when we write on top of it. So I'm just going to start over here and look at, okay, so a sub 1 plus a sub 2 will give us a sub 3. So that'll be the two terms previous will give us the third term. So the fourth term, we looked at 4, would be a sub 2 term and the third term. So we write it as a sub 3. The fifth term was that a sub 3, the third term, plus that fourth term. And we can go on to a sub 6, which is fourth term and the one previous. So to think about that, so it's the second previous one and then the previous one. So to get the nth one, what we want to do is we kind of use that thinking what we had is the nth one, but it's two previous of that. The previous one. So three term, we use the first one. 4 was 2 less was 2. 5 was 2 less is 3. So we take the nth term and we take 2 less than that. And then to get the previous one, we do n minus 1. I should have probably started with that one because that's the one we kind of know, and then do one more minus 1 to get that one. Now, we do have to start with, remember, this is our recursive rule, so we do have to have a starting term of 1, a sub 1 equals 1. And so and this is a very famous sequence called the Fibonacci sequence. And it happens and occurs all throughout the world and in nature and in space. And if you kind of search Fibonacci sequence, he was a famous mathematician, and it happens all through nature. So this is that rule, and it's only can be written as a recursive rule because you can't change this into a explicit rule because you need the two previous numbers added. So now let's take a look at, can we find the next three terms in this sequence? So if we think about this in a sequence number, so a sub n, so we're thinking about 1, 2, 3, 4, 5, 6. So we've got the sixth one. We want a sub 7. So we'll take the previous one, or the second previous one, the minus 2. So 7 minus 2 is 5. The fifth one, which is 5. And then we'll add it to the one previous, which is sixth term of 8, and that will give us the term 13. So a sub 7 is 13. Then it might be easier just to use these. So, but when you do that, you're using that recursive rule of 8 plus 13 down here. If we take 8 is that two terms before, 13 is the one before, to get the eighth term of 21. And the ninth term, a sub 9, would be the seventh term here, plus the eighth term. So that would be 13 plus 21 is 34. And so on and so forth. And those numbers occur and reoccur throughout nature, like a sunflower seed. It's in a sunflower seed. It's in a lot of flowers. It's in fruit like apples. It's in a lot of different places. It's in Beethoven and music. It's in our solar system. So those numbers show up in very many different ways once you start looking